Hello, good morning. I'm Roman and I guide you together with Janine through this webinar. The topic today is Microstructure Matters, Accelerating Battery Innovation with Digital Experiments. And I will start with a short introduction to this webinar. Why are we looking at this today? So we think that you need to design a good battery starting from its microstructure, but how exactly do you test the different microstructures? So the first step is you need to create the geometry that can be with different ways. Either you import a real 3D microstructure via CT scan or FIB-SEM, or you generate one. This is the way that we will go today. Then you need to analyze the microstructure in 3D. And here it's where you are leaving the common microstructure analysis world that you know maybe from other image segmentation software, because GeoDict is going ahead of this pure geometrical analysis. With GeoDict, you can do a performance prediction. So you can really get to know the key performance indicators. You can calculate effective conductivity, effective diffusivity to parameterize pseudo 2D Newman models, but you can also make a 3D resolved simulation of the charging with all the local information, lithium-ion concentrations and so on, of your electrode. And this we will see in the webinar. Well, developing batteries is a bit like a race. It's crucial to be ahead when you want to develop the best batteries. And the battery market is a very fast market. It feels like a race. You need to be fast to get your best product on the market. And we also are fighting a race against climate change. We need to get new technologies like electric mobility, and we need to get good batteries with low cost. And this is why we really need to get active here. But how do we do this? Well, the problem is that battery development is highly complex. And the reason for this is that you have so many parameters that are influencing the performance of your battery. First, the active material is important because it decides what's the chemistry. So do you use NMC for the cathode active material or LFP? What do you use for the anode? And next to the chemistry, the mixing ratio is really important. How do you mix the different active materials in your electrodes? How much binder, how much conductive additive do you add? There are so many possibilities. Then also with the particle shapes, even when you are using the same active material, the performance of the battery can be very different depending on the particle shape. So is it spherical particles, ellipsoidal? Is it more flake shape? But then also the particle size is one of the parameters. The porosity, which you can tune with the calendaring step in the manufacturing, or the thickness of the electrodes. And these are now only 6 parameters. And when you would only try 3 different possibilities for the parameters, you end up with 700 permutations. And if you imagine that you do all this in the lab, you already see that this is a very difficult task. But not only this, doing battery research in the lab is a very hard task because it's time consuming. You need to work with very expensive lab equipment, for example, in glove boxes or very dry laboratories, to avoid that the battery materials get contaminated by air, humidity, oxygen, or even nitrogen that can react with lithium. When you do high industry scale research, like here with this dry coating mixer, and you fill it with cathode active material, you can easily spend 30,000 euros for one run to try only one mixing formulation. And imagine that you test now 500 different combinations for your recipe, and 490 are dead end. This is a lot of costs that you don't want to cover. And in the end, the battery materials are also some toxic chemicals, and you have the toxic waste, which you need to handle in a responsible way, that the environment and the people working with it don't get harmed. And that's a problem. But what's the alternative now? Can you just shorten the lab experiments or you don't do them? I think that's not a good idea because you want to have a good product and you also want to have a safe product. and you don't want to have a faulty product that in the worst case might catch fire in a car or other device. So we think that you need to design a good battery starting from its microstructure, and it's a bit like when you want to build a nice house, then you start by designing a nice floor plan. And we think that you should transfer this when you develop a battery. So here we see the microstructure of a cathode. It was measured with FIB-SEM. You can have a look on this with so when you separate the different components, you see that there's the active material that is storing the lithium ions. Then you have the electrolyte phase in the pores. And here it's important that this transmits the lithium ions. And we have the binder phase with the carbon black. And this is important for the electron conductive network. And all needs to be optimized that all these different pathways work properly. But the question is, how can you do that? And there's good news. There is a solution that helps you to do exactly this, to design and test your battery on this microstructure level. And this solution is called GeoDict. GeoDict is our digital material laboratory, and you can find the best possible material without shooting in the dark, but rather you go through digital material design and analysis. This way you can design the best battery that matches your requirements. But how does this work? So first of all, you start with the material properties, and GeoDict has a material database for this. There are different kinds of materials used in batteries already stored inside. So there's different kinds of NMC, LCO, LFP, LTO, graphite, silicon, and so on. There are liquid and solid electrolytes, but you can also add your custom materials. And today we will use NMC as cathode material and a liquid electrolyte as they are stored in the database. Then you need a microstructure, and together with the microstructure, you get a prediction of the material performance. And this is also something that we will have a look today on the electrochemical performance of a cathode. But how exactly do you test the different microstructures? So the first step is you need to create the geometry that can be with different veils. Either you import a real 3D microstructure via CT scan or FIB-SEM, or you generate one. This is the way that we will go today. We use the microstructure generator tool from GeoDict to generate a cathode microstructure. Then you need to analyze the microstructure in 3D. And here it's where you are leaving the common microstructure analysis world that you know maybe from other image segmentation software, because GeoDict is going ahead of this pure geometrical analysis. With GeoDict, you can do a performance prediction. So you can really get to know the key performance indicators. You can calculate effective conductivity, effective diffusivity to parameterize pseudo 2D Newman models, but you can also make a 3D resolved simulation of the charging with all the local information, lithium-ion concentrations and so on, of your electrode. And this we will see today in the webinar. Yeah, and with this approach, you can basically test thousands of different microstructures, and then you can find the best compromise between the capacity, the performance, and the durability. And this would simply not be possible with laboratory tests because it would be too time-consuming. And in the end, you end up with promising candidates for the microstructure for your application, and then you know in which field you should focus with your experiments in the lab. So what's special about GeoDict? We think that you need a realistic model and a representative volume. And with other solutions, you maybe can generate only very rough microstructures, or you can only simulate a small volume that might not be representative for the electrode because the hardware requirements of 3D simulations are very high. But with GeoDict, we focus to get realistic microstructures with the structure generators, and also to have very high performance solvers for the physical simulations. So with modern hardware in a workstation that you can put below your desk, you can then simulate a large volume with a realistic microstructure that is representative for your electrode, and you get 3D resolved results. And today we will see how this works. Yeah, why do you want to work with GeoDict? You can first of all take better decisions. You move from guessing what could be the best microstructure for my application and what are the bottlenecks. You move to knowing what is really happening in my battery electrode and how can I design the microstructure to get the best product. You reduce the costs because you can run the digital experiments in parallel and you only test the most promising candidates physically in the lab. And you have a highly reduced lead time because you can test 100 different designs in only one day. And when you do that in the lab, you can maybe test only 3 different designs in 1 year. GeoDict is already very widely used in material research and development. There are 890 publications from engineers and scientists all over the world who are doing research with GeoDict, and 150 of them are in the field of batteries. We are also very proud that 5 from the 7 biggest cell producers are using GeoDict already. And yeah, let's now get started and look at the tool that you can see yourself.
Hello everyone and welcome to the online seminar Battery Modeling and Charging Simulation from Microstructure to Performance. My name is Janine and I will introduce you in the functionalities of the BatteryDict module. First, I want to thank the whole electrochemistry team for all the help during the preparation and everyday work. Ilona, Roman and Steffen are from the sales team and care for the customers. Fabian, Sebastian and Sven are responsible for the software development in BatteryDict. Additionally, we also have our partners at the Fraunhofer Institute doing the development of the best micro and best meso solvers. In this seminar, we will create a cathode using a GeoApp. Then we will perform a half-cell charging simulation, meaning that we use a lithium reservoir as an anode. In the end, I want to show you an exciting new feature, which is the support of electrochemical impedance spectrum simulations, or in short, EIS.
Before Janine's presentation continues, let's give you a context where her demo will begin. We can't proceed with the simulations unless we have a special model or a geometry of our microstructure. That's why I want to introduce you to the geometry toolkit of GeoDict. Janine will begin her content with a demonstration narrated mouse click by click of how to create an electrode geometry. Users can create geometries of complicated anodes and cathodes with a variety of materials, and they can create stacked structures to simulate full cells as well. This geometry toolkit has the tools to create generic granular structures, sophisticated inhomogeneous structures with nuanced particle size distributions with compressive calendering if desired, like you see here, or take a completely different approach and compute digital twin models of sample that has been imaged in the lab from 2D images or 3D images. For today, Janine is going to proceed with a simple structure generator that doesn't take up much compute time, so we don't spend the bulk of the seminar waiting around for a few CPU cycles. Let's get back to Janine, and she shows how to use GeoDict to make a simple cathode structure.
So let's get started with the electrode generation. For this, we will use the Bimodal Electrode GeoApp chip with GeoDict. You find it here under GeoApp, Battery, Structure Generation. In the module section in the bottom left of GeoDict, we can now see the GeoApp selection for electrode structure generation. We select the Bimodal electrode and click Edit. The Bimodal electrode app generates an electrode structure which consists of up to 2 types of active materials: solid carbon black and binder domain and fluid electrolyte. The active materials are modeled as solid spherical, elliptical, or convex polyhedron particles, depending on the chosen electrode type. The recipe of the electrode considers the grain size distribution of the particles, the ratio between particle types, binder mass percentage, and target porosity or target area loading of the electrode. We generate a cathode structure, thus enter cathode GDR as a result file name, then select cathode as the half cell type, then set the domain size to 150 voxels in x direction and to 300 in the other two directions. BatteryDict always charges a battery in x direction. Thus, we model the structure with the thinner side in x direction. The electrode will only contain one particle type, NMC, with the d values shown here. We use the standard electrolyte and binder with a mass percentage of 10 and aim for a porosity of 30%. The maximum number of tries can be set to 1, since I tested before for which random seed the porosity will be matched. Otherwise, several structures are generated, and the one closest to the given value will be taken. Enable the random seed input field and enter 20. If not enabled, a different random seed is used for each generation run, similar as done for the usual GeoDict structure generators. Click OK and run. At the end of the run, a message appears, showing that the target values were reached. The result file is shown on the result viewer, informing about the reached porosity and loading. In the visualization area, the resulting cathode structure is shown. You can change the colors as desired at any time via the Codon Visibility tab. For me, we can see that the active material particles are visualized in light gray and the binder in dark gray.
Okay, so now we have the geometry, and Janine made the half cell. We have the cathode structure. Users can follow that protocol or countless other protocols for making geometries relevant for their research. Next, she's going to walk us through the click-by-click procedure to perform a charge electrode operation, which will be the investigation of just the electrode in a half cell against a reference lithium electrode. She'll take the half cell she just created and start by calculating equilibrium potential curve, which you see here in dark. This quick 60-second routine that will establish us the reasonable voltage interval as our constraints for the charging. Then she'll proceed to set a charge rate and run a lithiation simulation of charging the cathode. These kinds of digital experiments on the fully resolved active material scale let us observe how the voltage changes the state of charge, and importantly, let's ask probing questions about ionic concentration build-ups, like you see here, and map the ionic fluxes or electronic fluxes or the evolved heat at various states of charge. The fully resolved simulation with this granularity, field of view, and nuanced state changes can be accomplished by an 8-hour run on a modest laptop. Rather than starting at a progress bar, Janine will show us the results she computed in advance. Then we'll ask the question, what if we are not focused on probing the volumetric state of the system? What can we get if we aren't willing to invest the 8 hours on numerical modeling? What can we get for a cheaper 10-minute pseudo-2D Newman modeling run with homogenized values if we are willing to do without the state maps? Let's watch Janine demonstrate these features now.
Now that we have our electrode, we want to know how it performs while charging. We start with a fully resolved simulation on the microstructure. For this, here select Predict, BatteryDict. Then, in the BatteryDict module section, select Electrode from the first pull-down menu, and then Charge Electrode from the second. Click Edit to open the charging options. We will start with only computing the open circuit voltage curve for the electrode to learn about which voltage values would be a realistic range. Thus, we changed the result file name to Charge Electrode OCV GDR. In the first step, we can find the constituent materials for the battery cell. For a half-cell simulation, GeoDict adds current collectors, separator, and a lithium reservoir as an anode to our cathode structure to build a battery cell. Using the buttons at the top, we can define the parameters for these add-ons. Below, we have the materials for our current structure. For manual materials, we can define the role in the battery cell. For the database materials, this is already fixed. The electrolyte will of course be the electrolyte. The NMC will be the cathode active material, and the binder in carbon black will be binder. In the density tab, we can define the solid and fluid densities of our materials. In the last subtab, define the electrical conductivity for the materials. Since the electrolyte is an ion conductor, this is the ion conductivity. For the active material, this is the electronic conductivity. For our database materials, these values are already defined, so we don't have to change anything here. We go on in the Solver tab and select Calculate Equilibrium Potential Curve for the simulation type. As you can see, the Experiment tab and the output options are grayed out. Because we only compute the analytical potential for an infinitely slow charging and don't run a real charging simulation. Click OK and charge. Find the plot of interest under the Plots tab in the Result Viewer. Here we have the equilibrium cell potential for charging. It makes sense to choose the charging boundaries according to these values. Having voltage values smaller than 2.5 or larger than 4.7 will lead to error messages while charging. It also makes sense to not use the extreme values. In reality, the battery should also not be charged up to full 100% SOC or discharged until it's really empty. Usually staying within the voltage values for 5% SOC and 95% SOC is a good guideline. For a reasonable charging, we choose now a range between about 20% and 90% SOC, meaning voltage values between 3.5 and 4.2. Now back to the charge electrode dialog again. Change the result file name to charge electrode fully resolved. And go to the Solver tab again. Here, we now select the fully resolved simulation and use the Lear solver. The parallelization can stay at the automatic maximum, which is 8 processes for me because my laptop has 8 cores. We can see that the Experiment tab became available again. Thus, we go to that tab now and define our experiment parameters. We will lithiate the cathode with a charge rate of 1C. So the experiment type can stay as it is. For the start and end condition, we choose initial voltage and final electrode SOC. As already discussed, we set the initial equilibrium voltage to 4.2 volt and set the final SOC to 90%. Additionally, we check Use Lower Cutoff Voltage and enter 3.5 volt. The simulation is stopped when the first of the two stopping criteria is hit. If the charging simulation reaches 3.5 volt, it will stop even if it has not reached the 90% SOC yet, and of course also the other way around. Move to the Output Options tab. Here, we can control how many result output files to create. This is useful because the 3D volume files are very large files. it makes sense to decide how many files you need before starting the charging simulation. In our case, we will end up with 8 to 9 volume files depending on the applied stopping criterion. Since we are charging from about 20 to about 90% SOC, and a new volume file is written after every 10%. If the voltage stopping criterion is hit first, it will only be 8 volume files. Below, we can decide which 3D result fields should be saved. This is also useful to reduce the file size of the resulting volume files. If you are only interested in some of the possible result fields, you can deselect the others. For the seminar, we just keep them all selected. Under the last step, you can have a look at the most important equations used in GeoDict. If you have a look at the user guide, you can additionally find detailed explanations on the theoretical background of GeoDict. We can now click OK and charge. Since the simulation takes about 8 hours on 8 cores, I already prepared the result to show it you right away. After the simulation is finished, the result file is opened in the result viewer. The report gives us information about the battery. A current of 453 nanoampere was applied to the battery, and a charge of 2.8 e to the power of -7 ampere hours was transferred in the battery cell while charging. Here we see that the maximum capacity is 4.5 e-7 ampere hours, and a heat of 4.2 e-5 joule was produced. Next, let's inspect the resulting plots. Here we find many interesting result plots. The first plot is the cell potential of an electrode state of charge. Observe that the charging was stopped at 3.5 volt, and SOC of 90% was not reached. Next, from the pull-down menu, select the produced area normalized heat power over time. Here we can see how the produced heat first increases a bit, then is constant for a while, until it is finally increased significantly when reaching higher SOCs. We can view the lithium concentration, the potential, and the overpotentials. Here we only need the plots for the cathode and electrolyte, since the anode was only a lithium reservoir. We can simply right-click in the plot and deselect all anode plots. Now we inspect some 3D result fields. Go to the Data Visualization tab and select the last result. We can see that the voltage of 3.5 volt was reached at 87% electrode SOC. Click Load Cell 7 cap. In the opening dialog, we select which fields to load. Deselect all, but concentration solid and thermal power density. Click OK. Under the Structure tab, we can clip the structure to see the volume field and the structure together. For the Z direction, move the slider until the upper half of the structure is clipped away. Now switch to the Volume Field tab. Let's first visualize the heat production in the battery. For this, we select Thermal Power Density from this Color by pull-down menu here. Then we select Transparency for a nicer visualization. Since the heat production takes place in the active materials, we uncheck all other materials here. In the end, we only have ID11 selected for NMC. To have nicer colors for our result field, open the Color Map dialog by clicking Edit. Here, we first set the data range to manual. Now we can enter values for high and low threshold. We enter 140,000 and 0. For the colors, we click Load Color Preset, and here we select Hot, which is just fitting for a thermal power field. We have many other presets here, and we can also create our own presets. To improve the visualization of the heat sources, go to the transparency field and drag the right point upward as far as possible. Now the white parts of the volume field are not transparent anymore. This increases the focus on the heat sources, which are now visualized in white. After closing the color map dialog, we will now additionally change the background color to black, so that the white parts of the volume field are perfectly visible against the background. Now in the visualization area, we see the produced heat in the active material of the cathode. There, the most of the heat is created, as we have seen before in the result viewer plot. You see that most of the heat is produced at the interface of the solid electrolyte due to the lithium intercalation into the NMC. Next, let's have a look at the lithium concentration in the active materials. Select concentration solid here, and keep the transparency and the visibility the same. In the color map dialog, we need other threshold values. Enter 32,000 and 30,000. Observe the higher concentration at the grain boundaries. And overall, the concentration is higher at the separator. Now that the fully resolved simulation has finished, we will start the same simulation but using the homogenized model. This will be a lot faster, but we don't get 3D result fields and for some properties less accurate results. It is important to choose the suitable model considering the specific question you may face in your material development process. Let us take the example of a model for a steam train. The wood locomotive already has all aspects of a train model to allow the train to run. However, the model is simple and no details are seen. The second model is a Märklin train with a lot of details. However, it also is more complicated. Similarly, you can choose different models when you develop your battery with GeoDict. For the dynamic performance of the battery, you need an electrochemical model. A simple model is the homogenized model of BatteryDict, which is a pseudo 2D Newman model. GeoDict calculates the effective parameters of the electrode directly from the microstructure. The effective parameters necessary for the pseudo 2D Newman model are, for example, effective diffusivities, effective conductivities, and so on. These material parameters are then set up in GeoDict. It provides you a cell potential with short calculation time and is suitable for parameter studies. BatteryDict also provides the fully resolved model as already seen, and this gives you a very detailed insight into the processes of the battery. For example, local ion concentration by charging. We now already performed a fully resolved simulation, represented by the Märklin train on the right. For a comparison, we also run a homogenized simulation on our cathode. For this, load the electrode structure again by clicking Load Structure in the result viewer. Open the Charge Electrode dialog again and change the result file name to Charge Electrode Homogenized. Go to the Solver tab and select the homogenized simulation. The solver type is now Best Meso. Click OK and charge. This will be finished within under 10 minutes. But still, I will again simply open the already finished result file from my project folder. Now, both charging simulation result files are opened in the result viewer. Show both results at the same time, by pressing Ctrl and selecting both files here at the top of the result viewer. The Results Report subtab provides the first information on battery performance. Many parameters are identical, as for example the current and the maximum capacity. The transferred charge is also very similar. The difference in the produced heat value is already larger, since the microstructure has a larger influence on this value. The effective parameters are only computed for the homogenized model because they are needed to perform the simulation, while they are not needed for the fully resolved simulation. Switch to the Plots tab and have a look at the first plot. It shows the cell potential versus the cell state of charge. We can see that they look similar. For a better comparison of the plots, we can combine them into one. For this, select Combine Results and enter Charge Electrode Comparison as a result file name. Click OK, and now we have a combined result file. Look at the Plots tab and we find the plots combined. The plots cell potential over cell state of charge are very close. The plots for produced area normalized heat power over time differ more. The blue plots are from the homogenized simulation and the red ones from the fully resolved simulation. The other potentials differ significantly because the microgeometry has a large influence on the values. For a better comparison, right-click in the plot and click Edit Graph Styles. Here, uncheck Toggle Visibility for all graphs. Then for the total plots, check the Graph Shown box again for both simulations. Click Apply and Close. Now, only one graph is shown for both simulations. The battery geometry plots are the same because the plot is generated before the structure is homogenized. A new feature in GeoDict 2026 is the Charge Homogenized Battery command. Select the command from the pedal menu in the Battery Dict section and click Edit. Here, we don't need geometry anymore. With Charge Homogenized Electrode, you can run the pseudo 2D Newman model without calculating the effective parameters again. Instead, we can either enter the geometry parameters and effective parameters directly, or load them from an earlier charge electrode result. This saves a lot of computation time. Click Load Charge Electrode Result and select the Charge Electrode Homogenized result file. Now, all needed geometry and material parameters are loaded. Computing the effective parameters is the time-consuming part in a homogenized simulation. Using this new command, we only need to compute them once, and afterwards we can just use them in this dialog and change the experiment settings as needed for very fast simulations. Also, we could change the geometry parameters if we want to. We leave all the geometry and material parameters as they are and switch to the Experiment tab. Here, we still need to define our experiment parameters because they are not loaded from the charge electrode result file. For the start and end condition, we use the same parameters as before. So change to initial voltage and final SOC. Then enter 4.2 volt for the initial voltage and 3.5 volt for the cutoff voltage. The final electrode SOC we set again to 90. Change the result file name to Charge Homogenized Electrode 1C GDR. Click OK and run. After a very short time, we have reproduced the same result as before with the Charge Electrode command because the effective parameters did not need to be computed again. In numbers, the fully resolved simulation needed 8 hours, the homogenized simulation with computing effective parameters needed 10 minutes, And the homogenized simulation with already given effective parameters only needed 10 seconds. The benefit of this new command is now that we can easily change experiment parameters and get the results for parameter studies really fast. We will now change the charge rate. Open the options again and move to the experiment tab. Change the charge rate to 2C to try a faster charging of our battery. Change the result file name accordingly. Click OK and run. Now we can compare the homogenized simulations with the different charge weights with each other using combined results again. We call the new result file charge homogenized electrode comparison and click OK. As expected, we have a lower potential for the fast charging. Also, much more heat is produced.
Okay, so we are finished with the part where Janine shows the charging simulation. And just as a remark, so there were already some questions in the chat. And if you have a question yourself, you can also write to the chat and we will answer them. And yeah, after the content of the webinar, we will also stay some time that you can enter questions and we will answer them. We have learned now how you create the battery electrode microstructure and how we predict the charging behavior of the electrode cell in a fully resolved or homogenized P2D Newman model to parameterize your materials for the model. Often electrochemical impedance spectroscopy, EIS, is used as a non-destructive characterization method for battery cells. EIS is a powerful method as the timescales of the physical processes inside of the battery are separated, so you can distinguish the ohmic resistance of the battery from charge transfer processes or ion diffusion in the electrolyte or the active materials. When you evaluate the AES measurements at different state of charges, different operating temperatures, or after different aging, you can learn which physical parameters describe the processes in the battery. However, evaluating AES spectra is not a straightforward task. In practice, researchers fit the AES spectrum with an equivalent circuit, a set of resistors, capacitors, and Warburg elements that mimic the real cell. But such an effective circuit is always a simplification of the battery. The results will strongly depend on what equivalent circuit you choose and transfer the findings of the equivalent circuit model to a more complex charging model, such as the P2D Newman model or the 3D resolved microstructure model used in GeoDict can be a hard task for the researcher. To this end, Janine will show you in the following the new AES feature that is available in GeoDict 2026 via a Geo app. With this functionality, you can simulate the AES spectrum of the battery and electrodes with the very same model that is also used in the charging simulation. This workflow should help you obtain a more accurate physics-based description of your battery without the usual back and forth between circuit fits and full cell models. So let's have a look at this now.
In the end, I want to show you an exciting new feature, which is the support of electrochemical impedance spectrum simulations, or in short, EIS. With this type of simulation, you can predict complex valued resistance called impedance, which is important for battery developers and scientists to understand the behavior of electrical components. EIS simulations can be performed on battery and electrode structures. The solver is controlled with a special charging profile over time, and the response of the battery structure is analyzed in a post-processing step. This allows to predict complex valued resistance, which is plotted with Nyquist and Bode plots. An example of such a Nyquist plot is shown on the right, where you can observe the impedance, for example, real and imaginary part, for different frequencies. The impedance is shown for the full cell, but also split to anode and cathode contributions. This feature is currently only available for the BEST solver. To use this feature, you can use the new Geo app. Later this year, we will create a tutorial explaining how to use this feature. This is the end of this online seminar. I hope you enjoyed the content. Thank you very much for your attention. Bye!
Thank you very much for the attention, also from my side. Thank you very much. If you have any remaining questions, you can always hop on our website, geodict.com, and then look for the contact form and write us and get in contact with us. Thank you very much. Have a nice day.